This is chapter 5, part 3, and we're going to continue by fitting the ARMA 2.1 model that was suggested by the AIC table that we just saw at the end of part 2. And so here we go. We're going to run the ARMA function with order 201. And here's the output that we get. And we see we get, well, we get the estimated AR1 and AR2 coefficients. The MA1 coefficient is exactly 1, which is on the unit circle. So that should give us cause for some thought. And well, we have the AIC value, the log likelihood, the estimated noise intensity. And let's investigate this fitted model. So the natural first thing to do is to examine the roots, and the AR roots are just outside the unit circle. So we have a stationary causal fitted ARMA model, but only just. As we saw from the last slide, the MA root is -1. So the fitted models at the threshold of non-invertibility, and a question is whether we have a non-invertibility problem. Okay, so let's just correct this while we're at it. Do we have a non-invertibility problem? So and one possibility is that the true MA parameter is close to 1, and another possibility is that there's something funny going on. When we go back to the previous slide, we see the standard error on the MA1, and it's pretty close to 0. So it looks like we can estimate that coefficient well, and we're pretty sure it's close to 1. But let's investigate whether this standard error is actually good. So the first thing we can do is see if the profile confidence interval is in agreement with this Fisher information confidence interval that the ARMA function gives us. To calculate the profile likelihood, we need to maximize the ARMA likelihood while fixing the things we want to fix at a range of values. And here we're going to profile over the MA1 parameter. So we want to fix that at a range of values and maximize everything else. And here's how you do that. This is just a kind of exercise in using ARMA. You need to use the fixed argument, and then you need to figure out what it fixes. Well, we're going to fix it turns out that in the syntax of fixed, it's the AR coefficients, then the MA coefficient, then the intercept. And you can't fix sigma squared, you have to estimate that. And we want to maximize over the ARs and the mu, so those go as NA and fixed. And that turns out to be how you calculate the profile likelihood. So let's go ahead and see what you get. Here we go. We've got a profile log likelihood over the over the MA1 coefficient, and we want to interpret this. Well, when you want to interpret a profile, you kind of go 1.92 down from 24. That would be 22.2. So that's down here somewhere. (1.92), and that's the confidence interval cutoff. Right. So we see the profile confidence interval is the whole interval. Well, I haven't plotted what happens left of 0.2, but you can see that it flattens out. Is the whole interval since the range of the profile log likelihood is less than 1.92. Now, by contrast, we can draw on the Fisher information confidence interval. So here's the cutoff. The Fisher information makes a quadratic approximation at the maximum, which looks like this. And the Fisher confidence interval quadratic approximation to the profile as shown which is much narrower because this quadratic, the true profile spreads out long before it gets to this minus 1.92 below the maximum cutoff. Okay. What do you conclude about the Fisher information confidence interval proposed by ARMA? Well, clearly the quadratic approximation is poor. To the profile. So the Fisher CI is unreliable. Now, when you have when there is much data, let's say, or a simple quadratic log likelihood then Fisher's method should work. This is a kind of pathological situation. I don't want to give you the idea that Fisher's method is never good. In many situations, it's entirely adequate. Okay, so we've seen that Fisher doesn't look very reliable. That doesn't really prove that the profile method is doing a good job. Remember that the sort of asymptotic justification for this 1.92 cutoff is really the same as the asymptotic justification for Fisher. So maybe if one's broken, the other's broken too. How can we investigate this? Well, let's say, we can do a simulation study. And we can think about exactly what that simulation study should be. Here we go. So our simulation study we are we're going to set the seed. That's setting the random number seed. That's really a convenience thing to make our number, to make our experiment reproducible. And we can decide how many simulations we're going to do. Here, J is 1,000. We're going to simulate from the fitted model. So our parameter vector is going to be the just the estimated coefficient of from the ARMA 2.1 fit to the Huron data. And then we can extract the AR and MA components for that. And we can stick all that into arima.sim, and that will give us a simulated data set from the fitted model. And then we re-estimate that at order 201 using ARIMA and take the fitted theta from that, and we'll call that theta j. Then we can take a histogram of all the fitted MA1 coefficients. So these are estimated MA1 coefficients when the truth is the fitted value. And here you go. This may look a little bit like the profile plot to you. It seems consistent with the profile plot, even when the truth, in fact, is 1 for the MA1 coefficient. Even though the standard error was very small, if we re-estimate from simulations from that, we get a range of MA values showing that we can't really be so sure what the truth is from that fitted value. Here we've done a histogram. If you do a density plot, it shows the similarity even more clearly. Oh, one thing this shows you is that because R will automatically fit you an invertible ARMA model, so the MA component will always be invertible. So in the MA1 context, it'll always give you an estimate between -1 and 1, so that the estimate is within the unit circle, so the root is outside the unit circle. Okay, here is a smoother density estimate plot. When you smooth, some of the density goes outside the unit interval. Now, one thing I should say here, I've written the code very simply. I haven't tried to tidy it all up. I haven't tried to relabel the axes and so on and so forth, worry about what the captions should be. If you were writing a report, you would improve on the default axis labels and title. Okay, so I just mentioned that the ARIMA will always estimate theta 1 between -1 and 1. It's really a very minor technical issue to worry about the fact that this density estimate estimates a curve that takes you outside the range of the estimated parameters, which is -1, 1. But it's a little detail that'll pop up in the course later in other ways. So let's start thinking about it now. And how would you refine this density estimation procedure to respect the range of the parameter estimation procedure? Well, I guess what we could do, we could use a parameter transformation, the game here which maps the interval -1, 1 to the whole real line, then we could do the density estimate on R which has no boundaries. Then we map back to -1, 1, the original scale of interest. I'm not giving details on that now, but if you want to think through how you would implement this and code it up, you're welcome to do that. Okay. Remember our second best model was by AIC was ARMA 10, which is AR1, and it turns out to be instructive to try simulating from this model too. So that's what we're going to do next. While we're at it, we're going to pick up another skill that we're going to need later, using multiple cores for simulation studies. Now, multi-core computing is helpful as you get to do more advanced modeling, larger, more complex models, particularly when you're doing simulation studies. It just lets you use the power of the computer you have, which has multiple cores. And at least in some contexts, like simulation studies, this turns out to be pretty simple to do in R. All you have to do is tell R to go look for your available processors and then send the jobs off to them and collect what comes out. And the do parallel package, which is a base package in R, you don't have to install it, it does that. And so here's how you use it. You call it with library do parallel, that imports it, and then you tell it to get to work with register do parallel. And the main thing you need, this is very much like the previous simulation study with just a few differences. So we're going to fit a 100 model here. And then we're going to re-estimate a 201, because we're still interested in the behavior of fitting the 201. We're just going to do it when the original fitted model is 100. So so the truth is 100 and we're fitting 201. So when the truth is 100, we know that the true MA1 coefficient is 0. And so the other thing that's new here is we're using for each, and you notice the syntax of here. This tells for each to do a parallel for calculation, where it just sends out each time it has to do a new simulation, it'll send it out to an available processor, whichever processor is available right now on your machine. Okay, another little coding detail. Some of these ARMA calls did not successfully produce parameter estimates. Why would it do that? It would be because for some reason it wasn't numerically convergent. And This little coding trick of using the try function lets the simulation proceed despite these errors. And then if it has an error, rather than crashing, it returns something called a try error, which firstly doesn't count, doesn't crash. Secondly, you can count it up and see how many of them there are. So 7 of the 1,000 simulations just were non-convergent. For the remaining ones, you can look at the estimates of the MA1 component. Remember that in this simulation study, this is the truth. MA1 is 0 for an AR1 model. And you see here that even when there is no MA1 model, if you fit an ARMA 2.1 to an MA1, then it's not that, then the estimated MA1 is spread out right across the interval -1 to 1, and actually it's quite likely to land exactly at the endpoints. Okay, so we think we understand better now that maybe it's just a spurious finding that when we fitted an ARMA 2.1 to the Huron data, we ended up with an estimated MA1 coefficient. We don't, MA1 is 1. It doesn't give us very much confidence that that's the actual model. Now, I said actual model as though there were an actual model. Of course, really one should probably say it's not necessarily an appropriate model. Okay, so when the true model's AR1 and we fit ARMA 2.1, we often obtain a model with estimated MA1 coefficient on the boundary of invertibility. And other than that, it's often kind of spread across. That means, since what we observed when we fitted ARMA 2.1 to the data was exactly this boundary case, we can't really reject the AR1 hypothesis, even though the Fisher information gave us strong evidence the data should be modeled with a non-zero MA1 coefficient. If you took that standard error from the fitted ARMA 2.1 at face value, it may be sensible to avoid fitted models too close to the boundary of invertibility. We've talked a little bit about why that is. You get unstable estimates of residuals, for example, and this is a reason not to blindly accept whatever model AIC might suggest. You've got an AR1 model that's only slightly worse AIC than the ARMA 2.1, but doesn't have this slightly unpleasant feature. So what else could you look for to help diagnose and understand this type of model fitting problem? Well, if you look again at the roots of the fitted ARMA 2.1 model, you will you'll see if you check in the ARMA 2.1 fitted model, you find close roots right. So the MA1 root, which has an estimated corresponding to the estimated coefficient of 1, almost cancels one of the AR1 roots. So if you notice that from the original fitted model, then maybe what happens later wouldn't have been a surprise. It's when you have almost cancelling roots, things are almost unidentifiable. And at that point, the ARMA 2.1 model, once you lose one AR root and one MA root, the ARMA 2.1 collapses to an ARMA 1.0, which was our next best model. Okay, so we've seen the possibility that in a fairly routine data analysis, definitely the sort of thing that you might find yourself doing when you're trying to analyze many kind of time series, you can start finding these cancelling root issues. Now, there are other numerical issues that come up with ARMA modeling. And so let's think a little bit about assessing the numerical correctness of evaluation and maximization of the likelihood function. This is a separate issue from the roots, because even if the numerics is perfect, and that really is the true maximum likelihood estimate to a very high number of significant figures, you could still have cancelling roots. This is saying that beyond the possibility of cancelling roots, we want to consider also the possibility that the maximization that ARMA does is imperfect. At least, and we're going to find that something is imperfect, and we're going to suppose, I think it's a correct supposition, that there's negligible numerical error in evaluating the likelihood. So likelihood evaluation for ARMA models is a linear algebra computation that should be pretty stable unless you're very close to a singularity. If you have cancelling roots, you do have such a singularity, so there could potentially be numerical issues there. Numerical optimization, however, is much more problematic, I think, in this context than evaluation of the likelihood. So how does the numerical optimization happen? Remember, we haven't even talked about exactly how the likelihood is calculated yet, and we're just leaving this ARMA function to do all the likelihood calculation and maximization without knowing the details of how it does it. But what you find out is that how ARMA does the maximization, it uses a general purpose optimization routine called optim in R, which doesn't use any special feature of the ARMA likelihood. It just produces a function that evaluates the ARMA likelihood and then plugs that function into optim. The likelihood surface can be multimodal, have nonlinear ridges where AR and MA roots almost cancel, and no numerical optimization procedure is reliable for maximizing awkward, non-convex, multimodal functions. And if you want to look for evidence of imperfect maximization, you can find it in the AIC table. This is the same AIC table that we saw a few slides ago. And if you want to look for inconsistencies, so the main insight given in this hint is that if you have nested models, making the model bigger can't give you a lower maximized log likelihood, because the smaller model is contained within the bigger model. That's what it means to be nested. And the definition of AIC is minus twice maximized log likelihood plus twice number of parameters. So if you go to a bigger model, then the worst thing that can happen if the mathematics is correct is you can get an extra penalty. If you have one more parameter, you'll add 2 to the AIC and so on. So let's write that down. Each extra nested parameter cannot mathematically increase AIC by more than 2 units, even though it were useless. And sometimes this happens. Let's find some, where does this happen? For instance, here, for example, adding one parameter from ARMA 2.2 to ARMA 3.2 adds greater than 2 units to AIC. It's not mathematically possible if likelihood evaluation and maximization were all correct. Let's say, boom, boom. Therefore, there is some numerical error, and this is not unusual. Again, this is not a very special data set. When you start analyzing your own data sets, I think it's a pretty good chance you'll find this stuff happening. And it's the conclusion is not to have total faith in the maximization. You should, as a careful statistician, you have to know when to be a little bit skeptical, and this is one of those times. That's the end of part 3 of chapter 5.